China spent billions trying to copy this machine and failed. Not Russia, not America, not even the world's biggest tech companies could replace it. Yet today, the modern world depends on it. Your phone, artificial intelligence, military systems, hospitals, banks. Almost every advanced computer chip begins with this technology. And only one company on Earth knows how to build the machine behind it. If these machines stopped today, modern life would slowly begin to break down. So how did one company become impossible to replace? How did the world become dependent on a machine most people have never heard of? This is the story of the machine holding the modern world together. These machines exist for one reason: to manufacture the tiny chips powering modern civilization. The semiconductor chip, a piece of silicon so small, you could fit 10,000 on a human fingernail. A single modern processor contains more transistors than stars visible in the night sky. Phones buzzing, traffic lights cycling, planes lifting off runways. Stock markets opening, trillions of dollars moving in milliseconds. A surgeon guiding a robotic arm through a procedure with impossible precision. A soldier navigating by satellite in a desert landscape, guided by chips. Modern civilization does not run on oil anymore. It runs on semiconductors. Remove these chips, and we revert to 1980. No GPS navigation, no internet, no modern medicine. No digital banking, no artificial intelligence, $14 trillion, gone. But as the world demands faster AI and more powerful devices, we face a wall. A physical wall, the laws of physics themselves. For decades, chip makers printed circuits using ultraviolet light, a process called lithography, like photography, but creating instead of capturing, printing on silicon at scales approaching individual atoms. You cannot print smaller than the wavelength of light you use. By the early 2000s, the semiconductor industry had hit that wall. Moore's law, chips doubling in power every 2 years, was about to die, unless someone could do what physicists believed was impossible. Unless someone could harness extreme ultraviolet light. EUV light, a wavelength of just 13 nanometers. 13 billionths of a meter, so energetic it defies intuition. But EUV light is almost impossible to work with. Air absorbs it instantly. Glass absorbs it. Traditional lenses cannot focus it. To generate EUV light, a laser must fire 50,000 times per second. At a droplet of molten tin, just 30 micrometers wide, falling through a near-perfect vacuum. The laser strikes twice. The first pulse flattens the droplet. The second turns it into plasma, hotter than the surface of the sun. 40 times hotter than the surface of the sun. That plasma releases EUV light, the key that unlocked the future of chips. That light is guided by mirrors, not ordinary mirrors. Mirrors polished to atomic-level precision. If scaled to the size of Germany, the largest imperfection would be 1 millimeter. The lasers come from one company, in California. The mirrors from Carl Zeiss in Germany, perfecting optics since 1846. The precision sensors from one company, in Japan. 3 companies, 3 countries, 1 machine. And at the center of this impossible machine stands one company. A company hidden inside a quiet Dutch town few people have ever heard of. ASML. 400 years ago, the Dutch built an empire through trade. Today, history returns in a different form. This is the story of ASML, the invisible empire controlling the modern world. ASML orchestrates a global supply chain of 5,000 suppliers. Across 20 countries, a network 30 years in the making. A network that could not be reconstructed from scratch in less than a decade. Not because they lack money. Not because they lack intelligence. The brightest engineers have tried. Because you cannot simply decide to build what ASML has built. The knowledge is embedded in people. In decades of failures that taught lessons no textbook contains. This knowledge can only be accumulated. It can never be copied. This is the invisible foundation upon which the entire modern world is built. But monopolies like this do not appear overnight. They are built slowly, through risk, failure, and decisions others were too afraid to make. And the story begins in the Netherlands in 1984. It's 1984, rain falls on Eindhoven, and Europe's tech crown is slipping. Philips, once a giant, is suddenly fighting for survival. Japanese competition is crushing Europe's consumer electronics industry. The Japanese leaders are faster, cheaper, and far ahead in manufacturing. Profits collapse, confidence collapses, the future looks uncertain. Philips makes a desperate move, a joint venture to bet on chips. The new team begins in cramped rooms, surrounded by equations. Their mission is clear: build lithography machines for chip making. The market belongs to powerful incumbents with decades of dominance. This Dutch newcomer is ignored, underfunded, unproven, dismissed. Some years, survival feels like the only victory. Then ASML makes a decision that changes everything. They choose openness instead of secrecy. While rivals guard everything, ASML invites customers into the project. One major customer invests, buying influence, not just machines. Another invests too, tying its future to ASML's success. A third joins. Customers become partners, and partners become loyal. It's a radical strategy. Make your customers your shareholders. Let them steer the roadmap, and they'll defend it. And against all expectations, it works. Through the 1990s, ASML grows, quietly, steadily, relentlessly. Each generation improves. Each upgrade wins another foothold. Market share shifts, slowly at first, then unmistakably. Then comes the choice that changes the entire industry. By the late 1990s, everyone sees the physics wall approaching. Many alternatives are tested. None can carry Moore's law forward. The incumbents study EUV and decide it's not worth the risk. Too costly, too uncertain, too far from what they know. ASML stays, alone with the impossible. For years, the project looked impossible. Investors doubt, engineers struggle, the project refuses to die. Some believed EUV would never leave the laboratory. In the 2000s, EUV consumes resources far beyond ASML's size. For years, the light is too weak to matter. For years, the mirrors degrade faster than anyone predicted. Every failure delays the future of computing itself. But every failure also teaches something no textbook can. Meanwhile, in California, a laser company works for decades. One obsession: EUV power strong enough for factories. To generate EUV light, a laser must fire 50,000 times per second. Hit a droplet of molten tin smaller than a grain of sand. Generate plasma hotter than the surface of the sun. And repeat the process continuously without failure. In 2010, ASML buys that laser knowledge outright. It's a bet the company move, and there's no turning back. billions are poured into a technology no one knows will succeed. Slowly, the impossible machine begins to improve. Engineers stabilize the light source. Mirror systems achieve atomic-level precision. Then a breakthrough. Power levels finally reach factory reality. Then, in 2012, ASML's biggest customers make an extraordinary decision. They invest billions directly into ASML. Because the future of their own companies now depends on EUV succeeding. The entire semiconductor industry is now betting on one machine. That money buys what competitors cannot replicate: time. And time is where technological monopolies are built. Then, after decades of failures, the breakthrough finally arrives. By 2017, a production-ready EUV machine stands complete. The machine is unlike anything humanity has ever built before. It weighs 180 tons, built from thousands of precision parts. This machine contains over 100,000 individual components. Every system is tested at the edge of physics. One machine needs multiple cargo flights just to arrive. Hundreds of crates arrive under extreme security and precision handling. Installation takes months, calibration takes months more. Because nothing this complex is simply turned on. To generate EUV light, a laser must fire 50,000 times per second. The second turns it into plasma, hotter than the surface of the sun. Mirrors polished at atomic precision guide that light onto silicon wafers. The patterns printed are thinner than individual viruses. Every step pushes engineering beyond previous physical limits. Then the first EUV-produced chips finally emerge. Smaller, faster, more powerful than anything before them. The semiconductor industry immediately understands what has happened. The physics wall has been broken. And only one company knows how to cross it. Demand explodes across the global technology industry. Every major chipmaker wants access to the new machines. Orders stretch years into the future. Production slots were effectively sold out years in advance. It cost $150 million, and customers still say yes, to nearly $400 million for the newest generation. Customers accepted those prices without hesitation. Because falling behind now means technological irrelevance. Every advanced semiconductor company becomes dependent on ASML. Taiwan's advanced fabs run entirely on these tools. South Korea's advanced fabs run entirely on these tools. America's advanced fabs run entirely on these tools. Every artificial intelligence model depends on chips born here first. Modern fighter aircraft processors are born from the same technology. Global finance moves through processors designed at atomic scales. The modern world quietly reorganizes itself around one technological choke point, and most people never even hear its name. This is the story of ASML, the invisible empire controlling the modern world, a company that now controls the gateway to the future of computing. But once technology becomes this important, it also becomes geopolitical. Power over the modern world now runs through 3 capitals and 1 quiet Dutch city. Washington shapes the technological future through policy and restriction. Beijing races to break dependence on Western semiconductor technology. But the true center of technological control lies far from global attention. In a quiet Dutch city, one company controls the world's most critical machines. And by the early 2020s, governments begin treating those machines like strategic weapons. In October 2022, a decision changed the balance of technological power forever. The United States imposed restrictions targeting the world's most critical semiconductor supplier. ASML was banned from selling its most advanced machines to China. This is not a trade disagreement. It is a fight over who controls the future of computing itself. Because advanced chips now determine economic power, military power, and artificial intelligence leadership. Without cutting-edge semiconductors, modern AI cannot advance. And without ASML's machines, those semiconductors cannot be manufactured. One company has become a choke point in 21st century geopolitics. China responds with enormous urgency. Billions have been allocated towards semiconductor independence. Billions flowed into research laboratories and fabrication facilities across the country. Engineers worked relentlessly to close a gap measured in decades. But semiconductor leadership cannot be built overnight. ASML's advantage is not based only on patents. Engineering mastery cannot be purchased instantly. It must be earned. Thousands of specialists held together by one ecosystem. The supply chain spans continents and generations of engineering expertise. No amount of money compresses 30 years into 5. And no political will can override physics itself. Meanwhile, demand for artificial intelligence chips surged worldwide. Data centers expand faster than semiconductor production can keep up. Every AI breakthrough requires more advanced chips. And every advanced chip requires ASML's machines first. Demand surges beyond what the company can physically produce. The backlog of orders stretched years into the future. Every machine leaving the factory is already sold. The monopoly is not weakening under geopolitical pressure. It is becoming even more essential. The world is now building its future on a supply chain controlled by one company, and that creates a dangerous question. What happens if the world's most important machines suddenly stop? Not destroyed, not erased, simply interrupted. A cyber attack, a supply chain disruption, a geopolitical crisis. Modern civilization is far more fragile than it appears. Modern civilization depends on uninterrupted semiconductor production. And semiconductor production depends on an invisible chain few people understand. Factories across continents would begin slowing production within months. Reserve capacity would delay the consequences, but not prevent them. Artificial intelligence expansion would halt without advanced semiconductor supply. Military procurement would face unprecedented delays and shortages. Medical equipment manufacturing would slow dramatically. Economic losses would reach trillions of dollars globally. Because modern civilization now runs on semiconductors. And the world's most advanced semiconductors are concentrated in a few fragile locations. Taiwan produces most of the world's leading-edge chips today. Those fabrication plants operate at the absolute frontier of engineering. Their output powers nearly every advanced technology on Earth. But every one of those factories depends on machines built in one Dutch city. Geography has concentrated enormous technological power into a fragile global system. Governments understand the danger. Billions are now being invested into new semiconductor factories worldwide. America is building fabs, Europe is building fabs, Asia is expanding even faster. New factories alone cannot replace critical lithography technology. Every new fab still requires the same lithography systems. In fact, every expansion deepens dependence on ASML even further. The more the world advances, the more essential this choke point becomes. And ASML is already building the next generation of machines. Systems capable of printing features at near-atomic scales. Machines so advanced that no competitor has come close to matching them. The technological moat continues widening with each passing year. Because this monopoly is not built on marketing or branding. It is built on accumulated knowledge. It exists in people, experience, and accumulated engineering failures. This knowledge cannot be copied instantly or purchased easily. This is what power looks like in the modern age. Not territory, not armies, not flags. But control over the technologies civilization depends on most. Empires once ruled through armies and territorial control. Today, power flows through knowledge and engineering precision. Through invisible machines operating inside sterile rooms. Machines most people will never see. Yet machines that quietly shape the future of the entire world. Few people recognize the source of this invisible power. The company behind it rarely appears in headlines. Yet its influence defines the limits of technological possibility. Every chip begins its life inside these precision machines. Every artificial intelligence model depends on its precision. Every advanced weapon system relies on its output. Every digital economy runs through infrastructure it helped create. This is not simply a corporate success story. It is structural power embedded within modern civilization. Power that operates invisibly, but shapes global outcomes. Concentrated in one quiet Dutch city few people have ever visited. A single choke point in the architecture of modern life. You may never have heard its name before today. But everything you depend on, your phone, your bank, your hospital, your military, your future, already depends on it. ASML. The invisible empire controlling the modern world.